Okay, so um, as usual, quick announcements. This final homework before the midterm has been online. It's technically due today, but we've got the standard 4-day grace period on homeworks, and so it'll actually be due Saturday night, and the solution set will go live automatically Sunday morning. Once the solution set is out, I can't accept any more assignments, but as long as you get it in before Saturday night, then you'll get no late penalty. Histogram hints, if you're having, so in the past, it used to be, especially on Macs, a little bit harder if you used Excel to do histograms. Now, all of the nice histogram features from the Windows Excel have been imported into the Mac. So there are plenty of nice histogram features in Excel that you can use. So it's pretty easy to generate those histograms, but I've got some links to resources online, including some YouTube videos. I can show you how to do that if you're having trouble with that. When you do the histogram, make sure you histogram your random variate X and not your random numbers R. So if you get a uniform histogram out, like a histogram looks like a box all the way across, you've probably histogrammed the wrong column. So the histogram you should get out should look like the probability density function that you're designing for. So if you're to plot that PDF out, it'll have a particular shape, and that histogram should sort of look kind of like that. And we'll see that today. Your submission should be either as a document or a PDF. Please do not submit a spreadsheet with thousands of random realizations. You can upload the spreadsheet in parallel with the doc, but in the actual doc, which will be the main thing the grader will grade, then we're looking for plots and text. So it's as if you were writing this out, on paper. You might include a chart or a plot in what you're writing out, but you wouldn't include all whatever 10,000 lines of numbers. And so although including the spreadsheet with your submission is great to show your work, in the actual document, do not just copy all the numbers over as a table into your Word doc, because that's not really a useful deliverable. That's just sort of what I'm stressing down here. Otherwise, looking forward, there's this practice Canvas activity available. So again, this is a longer Canvas activity. It's due before the next lecture. It's meant to be midterm practice. It's longer than most Canvas activities because it samples from all of the previous Canvas activities. We can take it as many times as you'd like, and you'll get the highest score from that. Then Thursday, we'll have a midterm review. So pretty much just bring your questions. I will have prepared slides just in case there aren't any questions. We're going to just sort of hit what I think are the kind of the greatest hits of all the units that we've gone over so far, to sort of say, these are the things I really hope that you took away from the units to be in prep for the midterm. But if you've got a bunch of questions, we can just work those. If you want me to work out, examples on the whiteboard for like, things like this homework problem, we can do that. So, just sort of however you want to use that time, but that'll be Thursday, right? Thursday of this week. And then Tuesday of next week will be midterm stage 1. The availability windows are posted on Canvas, but and again, I meant to double check that before I came here, but I just remembered it as I stepped out of the office. But whatever the availability window says on Canvas, that's the window where the midterm will be available for you to start taking. But then once you start taking it, you'll have 90 minutes, 90 to 75 plus 50 minutes for technical issues to complete it. And you do that all individually behind Respondus lockdown browser with camera. It's an individual exam, closed book, closed notes. You can have 2 formula sheets front or back. If you do that lockdown browser test, which you'll need to do like the compliance test to unlock the midterm module, then you'll see that there's a bunch of old exams, and I think maybe including even a practice one on Canvas that you can take a look at to sort of give you an idea of what is going to be on the midterm. Then Thursday, then you'll have the stage 2 exam, which will be a collaborative exam. So you can work with anybody who's enrolled in the class. That too has an availability window, which is longer than just that Thursday, but it's not timed. And so you can just work on it continuously or wherever you would like, however convenient, as long as your submission is in before the availability window closes. I will be here Tuesday and Thursday in the midterm periods in this class, only for the 75 minutes, because there's a class that comes in right after this. So if you want to take the exam on your laptops in this room with me here proctoring, that's fine, but you'll be limited to that 75 minutes because you got to kick us all out right when the class ends, because there's a class that comes after. So I will be here in case you want to work on stage 1. I also will be here for stage 2. So if you want to come in and use this 75-minute period to work together, so I'll just stay out of your way up here. And if you have any questions about the exams, like wording and things like that, I can help with. But generally, if you just want to use this as a time to all be in the same place, or a couple of people in the same place, then that's fine. Or you could just avoid class on both of those days and take them from the comforts of wherever you'd like to take them. So that's the kind of exam stuff. So are there any questions about any of that? Looking for questions online. Timeline pretty clear. Pause for a second. Okay, great. So in the last couple of lectures, we've been introducing ourselves to a variety of different probabilistic distributions that we can use as input models to our stochastic simulations. And so what we mean by input models are the sort of variation that we put into our logic that will end up being the reason why we get variation on the output of our logic. And so if I'm modeling a device that inspects cracks in an aircraft wing, and I need to model failure times that are exponentially distributed, that exponential distribution is an input model. And so I imagine a larger system that, say, monitors the aircraft wings, maybe makes repairs to them, flags them, et cetera. That larger system is the simulation logic. But then I need to know how often the aircraft wings actually fail. And that distribution is what we refer to as an input model, in this case, an exponential distribution. So that's fine, but then the question has to be, well, how do we generate an exponential distribution? And so we know that an exponential distribution is described by a probability density function like this. You take the area underneath it, we get a cumulative distribution function that looks like this. It's written in this form right up here. And so if we have that cumulative distribution function, it turns out that if we can generate a uniformly distributed random number between 0 and 1, we can use the inverse of the cumulative distribution function to turn the randomness in the uniform distribution into our desired randomness. And so this uniform stretch between 0 and 1 gets sort of stretched out here so that it gets compressed closer to the axis and it gets stretched out farther away in exactly the right way, so that even though we generated numbers from 0 to 1, after we put them through this transformation, we got numbers that are exponentially distributed exactly as we wanted them to be. So this gives us some mathematical. Yep, there's a question online.
Yeah, we can't see the slideshow.
Oh, okay. Sorry about that. Let me reshare.
Thank you.
If I can find. Thanks for speaking up. How's that? Is that showing up better?
Yes, thank you.
Great, thanks. Let me bring up the. And apologies for that. All right, so fortunately, just review so far. So yeah, we're just saying that this is how we get that exponential distribution out. So then the question then has to be is how do we start with, or how do we tab back over here? How do we get the uniform distributions? Well, that was the last time here, these pseudo-random number generators. So we need kind of an arithmetic way, because that's really all the computers are good for, is a numerical method, an arithmetic method, to generate something that looks random, even though it's not actually random. So we use mathematical expressions that are deterministic, but they're chaotic in that if you change their initial number, their initial seeds, you get very different outputs. And so we make use of that chaos in order to mimic randomness. And so we can start with a seed, and if we start with different seeds, we get different strings of random numbers. So the idea here is I could imagine starting with seed 1, 2, 3, 4, 5. If I start a random number simulation where the math is identical in the sim, but I just start with a different seed, then I'll get very different outputs out. And we can easily see this in Microsoft Excel, for example, because it doesn't expose the seed to you, the user. It instead seeds its random number generator with the time. And so every time you resave Excel, like so here I've got this, I've just done a rand in every cell in this first column, and I've got the exact same spreadsheet here. This is at 126, this is at 128, and every time I resave, it redraws all those numbers, and they look different because what changed was the time changed, and the time is the seed for the random number inside Excel. So in some ways, this is convenient because the average person, when they go into Excel and they type in rand, wants a new random number. For us as simulation engineers, this is kind of annoying because sometimes we actually want to rerun the same universe that we've built over and over again to better understand what happened. So in Arena or simulation tools,
or like
it sounds like somebody unmuted online. Is that just a mistake? Okay. So in Arena, what we do is we actually can access the seeds. And so inside Arena, each simulation replication uses a new seed, but every time you start Arena, replication 1 will always use the same seed. Replication 2 will either always use the same seed or always use a seed based on wherever replication 1 left off, and so on and so forth. So every time you open Arena, you're going to get replication 1 of the same simulation is going to have the same output. So if you have 60 students in a class and they all hit run on 60 different arenas, if you go to that report screen, you'll get exactly the same stats out, because unless you've modified the seed. Now, Arena gives you the ability to modify the seed. You can go in and you can drag in this seeds block, and we'll talk about this a little bit more later in the semester, and you can then edit or add streams, and the default stream is stream 10. So if you create a stream 10 here, you can then type in whatever seed you want, any 5-digit number, and then your simulation will have different results than your neighbor because their seed will be different than your seed. So that's a way that we can actually edit that. And so that's kind of all I'm sort of summarizing up here, is that Arena has 10 numbered streams, 1 through 10. You can actually even name streams. And then you can go through and you can, if you don't if you don't put a stream in to a Random-Variate inside Arena, it assumes it's stream 10. Otherwise, you can actually say, this part of my model is going to use this random number stream. This part of my model is going to use another random number stream. And there's various reasons why you'd want to do that, as we'll talk about when we get into variance reduction strategies in the bottom half of the semester. But for now, we're just saying that it just defaults to stream 10. So inside Arena, and I'll show you expressions today here, there's already some preloaded distributions like unif, triangular, exponential, normal, and each one of these have parameters you must put in, like the min and the max for the unif, but they have an optional parameter that follows them, which is the stream ID. And by default, it's 10. So if you leave it out, it'll go to 10. So if you edit stream 10, you can edit the seeds for that. But if you want to create your own random number streams with any number between 1 and 10 or some other name stream, you can actually put that name in there. And then that Random-Variate will draw its numbers based on an underlying, you can think of it a die roll that's using a die kind of customized to whatever seed that you want. So that's kind of what's going on there. So Arena gives you a lot of control over your random number seed so that you can rerun the same simulation over and over again and better investigate strange things that might have happened during certain simulation runs. So the key point that I want to give here is that you can control the random number seed in Arena, and for the same random number seed, if you go into the replication settings, which we should get familiar with after lab 5, if you set Arena to run for 10 replications, then when you hit run, it's going to run all 10 replications. Replication 1, 2, 3, all the way up through 10 will use a different seed, all within the same streams that you've configured. But then if you stop and then replay it, those 10 replications will give you the same outputs per replication. So the replications will differ because those replications use different seeds. But if you run the experiment over and over again, then replication one will look like replication one will look like replication one all the time because they're all using the same random number seed. 2 all looks the same, 3 all looks the same, and so on. And that adds reproducibility. So if you've got a particular performance result, it's easy to export to somebody else, and they won't just think that you're lying about the numbers or you got those numbers by chance, because if they run it with the same seeds, they'll get the exact same numbers again. So it really helps make us honest by having this reproducibility. All right, so that's what I mean by seeds. Now we talked about last time, and this is where we started to leave off here, is that the 2 important properties of random number generators are what we said was uniformity and independence. And so here we've got a good string of sequence of random numbers because we don't notice any clumping. So this looks uniform to me because it's kind of distributed all over the number line from 0 to 1. But down here, we've got a lot of numbers that clump together, say around 0.2. And so that tells me that they're not uniform. So this looks to me like a bad random number generator. Down here, this is independence. And so here, I don't notice any pattern if I look across the numbers here. 0.49 comes after 0.34, or 0.34 comes after 0.49. But if I look at other numbers that are close to 0.49, what comes after them is very different than that. So I don't see any pattern up here, but down here, I clearly see there's an increasing pattern. So even though there's uniformity, it's been sorted here. So if you take the same exact numbers and sort them, you get a violation of independence. And so likewise, if you take the same exact numbers that are sorted and you randomly permute them, then you can generate independence. And so independence is not about the distribution of numbers, it's about how one number relates to the next. And uniformity is not about how one number relates to the next, it's about the distribution. So we've got a distribution property and we've got sort of a correlation property. So are there any questions about those 2 properties, uniformity and independence? Those are the 2 most important properties of any pseudo-random number generator. So I want to make sure that we have those down. Okay. All right. So now we have to figure out, well, how do we test for uniformity if it's so important? How do we test for independence if it's so important? And this is where we started to go last time. So for uniformity, there's 2 tests that we talk about in this class. Things get a little more exotic as we go into, more in sort of things are outside of the scope of this class, but these are pretty well used. And so these are pretty good ones here. So if you have a lot of samples, use the chi-square test, which is probably something that you've had to work with in say 380, I guess, is where we usually put chi-square tests. Something you may not have seen before, but you've now seen on your homework is a Kolmogorov-Smirnov test. And so they both do roughly the same thing as far as we're concerned, but the chi-squared test only really works for large sample sizes. The Kolmogorov-Smirnov test only really, works best for small sample sizes, but once you're at large sample sizes, it ends up becoming more mathematically convenient to go with the chi-squared test. And we'll talk a little bit more about this after the midterm, but we're just focusing on uniformity here. So chi-squared test, this is hopefully mostly review. Maybe in 380, you might have said, well, use a chi-squared test to see if these numbers are Poisson distributed. Well, we're doing the same thing here, but we're testing for uniformity. So I could give you something like this on the midterm, where I say, here are 30 numbers. And so here they are there, just 30 numbers that are distributed between 0 and 1. Now, I would also on a midterm tell you that I want you to use a I might not tell you that I want you to use a chi-squared test, but I will somehow tell you that if you are to use a chi-squared test, I'll tell you how many intervals to use. So after the midterm, you get to figure out how many intervals to use on your own. Before the midterm, I'll tell you. So I'll say that, use 4 intervals to test for uniformity of this. And so what I mean by that is if these are uniformly distributed, then we would expect if you divide up these intervals of equal width, so each one of these are 0.25 wide, then I should get an equal number of numbers of these 30 numbers in each one of these on average. So that's what we mean by being uniform. If you've got the same size bins, you should get on average the same number of outcomes falling in those bins. So that's why I got in this point, this 4 intervals divided by 0.25. So now I need to count how many actually landed in each bin. Well, if I go through these 30 numbers, then I can see 3 landed in the first bin, 4 landed in the second bin, 8 landed in the third bin, and 15 landed in the fourth. Now already, this looks like it probably violates uniformity because 15 is a pretty big number. That's like half of all of the numbers. But I need to sort of rigorously say that because really this could have happened by chance. And so that's what the statistical test does. It really says is how often would you get this sort of result if they were uniformly distributed and you just had bad luck with this draw of 30 numbers. That's really what we're testing with the chi-squared test. So then we then have to figure out how many would we expect to see in each one of these bins. Well, that's easy for uniform. Just take the number of draws, 30. That's how many were up here, divided by the number of bins, 4. And so I would expect about 7.5 in every bin. So that's if this hypothetical distribution is uniform. Now, if this is not going to matter before the midterm, well, I mean, I guess I could ask you about something along these lines, but this will become much more important after the midterm. But if this expected number is less than 5, you cannot use a chi-squared test. After the midterm, we'll talk about the theory as to why. But if the expected number is less than 5, the chi-squared assumptions don't work and this test breaks down. So you have to make sure this expected number, not the observed number, but the expected number is 5 or greater for every bin. Once you've got that, you can calculate your chi-squared statistic. And that's just going to be the observed number minus the expected number squared divided by the expected number. Do that for every bin and add all of them together. And we'll talk about where that formula comes from after the midterm as well. For now, we just have to take it for granted that it's a good formula to use. Now, how to interpret this number that comes out of here? Most statistics, T statistics, Kolmogorov-Smirnov statistics, chi-squared statistics, are effectively distance from null. So if this number is large, it means you're far from the null. If this number is small, it means you're close to the null. And that should make sense because what we're really saying here is if there were 7 or 8 in every bin, well, then this number would be small. So, well, that's exactly what we'd expect if they were uniformly distributed. So that's what you should be thinking about. Like, did I reject the null or not? If you get a really large number, larger than the threshold I'm about to show, then you reject the null. If you get a small number, you fail to reject the null. So that's the last step in our chi-squared, is to look up the critical level that above which you reject the null. And for a chi-squared test, the way I read this table is I'm going to give you a level of significance, in this case, 5%. And so I look in a 5% column for level of significance. This is my type 1 error, my alpha. And then I need to look in the row here for degrees of freedom. The degrees of freedom for a chi-squared test is 1 less than the number of bins. So if you use 4 bins, I look in row 3. And so row 3, 5% column gives me a threshold of 7.81. That means that 7.81 is the maximum tolerable difference from the null before I reject the null and say, no, there's no way these numbers came from the null distribution. And I'll be wrong 5% of the time, but most of the time that will be a good inference to make. So that's all I've said down here. For alpha equal 0.05, the difference that we found here is greater than the threshold. So we reject the null hypothesis and we conclude that it is unlikely that these numbers were drawn from a uniform distribution. And any process that generated these numbers is not a good mimic of the uniform distribution. So any questions about that, about the chi-squared test? You feel like you could do that if I were to give you something like that on a midterm? It should be kind of review of 380 stuff. Okay. Questions online? Okay. All right, so then the other one that now you've hopefully gotten a little more experience with through the homework is the Kolmogorov-Smirnov test. This is what we do when we have small sample sizes where we can't meet the chi-squared's expectations of having an expected number in each bin of 5 or more. So how does the KS test work? Well, the KS test, all you do is you take your outcomes. In this case, it's the middle row here, all these RIs. Those are the outcomes I care about. Sort them. So you just sort them so that the lowest one's on the left, the highest one's on the right. And if they're uniformly distributed, then they should fall into a small window corresponding to their sort order. So if I have 5 numbers, then distributed uniformly from 0 to 1, then I would expect the first number to be somewhere between 0 and 0.2. I would expect the second number to be somewhere between 0.2 and 4, the third between 4 and 6, the fourth between 0.6 and 8, and the fifth between 0.8 and 1. So basically all the Kolmogorov-Smirnov test does is it just says, all right, let's look at these 5 numbers. Are they in the bins that we expect? And if they aren't, let's measure the distance kind of from those bins. And then again, we set up kind of a maximum tolerable distance, just like we did in the chi-squared test. And so that's what I'm doing here, is I say, well, I'm going to measure the distance from the top boundary, the distance from the bottom boundary. All right, so those will give me those 2 distances. Here, I measure the distance from the top boundary, 0.26, which will end up being the largest distance here. The distance from the bottom boundary, I don't even calculate because it's negative. And so because I'm going to be looking for the maximum distances, then whenever you see a negative there, I mean, you can calculate it, but it's just a waste of calculation because we're not ever going to pick it as the maximum. So that's why I just put a dash there. So I do that for each one of these pairs, and then I get the maximum distance from the top boundaries and the maximum distance of the bottom boundaries. And then I take the maximum of those 2, and I see the maximum distance from a boundary, in this case, is 0.26. Now, if I look in my KS test table, it's similarly set up where the columns here are my level of significance. So I go to the 5% significance level column. But my degrees of freedom here are the number of samples, in this case, 5. So it's not 5 minus 1, it's 5 exactly. And again, after the midterm, we'll talk about the math behind why it's -1 for chi-squared and not -1 for Kolmogorov-Smirnov. And we'll see that I get a threshold value of 0.565. So for these, this 0.565 tells me that this 0.26 maximum difference is pretty tolerable. So there is a good chance that a uniform distribution would generate numbers that would differ by 0.26. One of the features of the Kolmogorov-Smirnov test is it has high, what a term that we'll introduce after the midterm, statistical power, which means that when you fail to reject the null, you actually have more ability to accept the null. You don't have that with a chi-squared test. And so generally, fail to reject does not mean accept. But the Kolmogorov-Smirnov test is one of these special tests that is kind of so sensitive that if it fails to reject, you can have pretty good confidence, unless your sample size is really, really small, and maybe this is pretty darn small, that this is that the null hypothesis is a good approximation. So that's the KS test. If we want to see visually what it's doing, effectively the green line is the expected cumulative distribution function for a uniform. And the black stair-step line is the empirical CDF you get from sort of approximating the CDF from these numbers. So it's just sorting the numbers on the x-axis and plotting them against their normalized rank on the y-axis. And that gives you an approximation of the CDF that is being etched out by our samples. And what the Kolmogorov-Smirnov test does is effectively measures the distance from the expected CDF and a sample CDF. And we can see that the sample CDF doesn't wander too far from the expected CDF. And so because it stays close to it, then it feels like these really could be uniformly distributed numbers. So that's the KS test. Any questions about the KS test? The test we use for small sample sizes, it has high statistical power. And we'll talk about what statistical power is after the midterm. But for now, just know that we use it for small sample sizes. We use the chi-squared test for larger sample sizes. Okay. Questions online? And those are our two big tests for uniformity. All right, so the last two tests that we need to make sure we know about are tests for independence. Now, if you go back to the previous lecture, I've got a lot more slides on so-called autocorrelation tests, but which go into details about what it means to do an autocorrelation test. But in the end, it's not practical to use autocorrelation tests to test for independence the way we do. So I'm not expecting you to know how to do an autocorrelation test. But if you want to see examples of what I mean by one, I welcome you to take a look at the slides from the last lecture. But the overview here is that if I have a sequence of random numbers, I can ask how well do one number in the sequence correlate to numbers a few down from it. And so what I can do is I can say across all of the numbers, what is the correlation between this sequence and the sequence taken when I shift the sequence over by one step, or the sequence over by 2 steps, and so on and so forth. So I can just plot like a regression line where I can form pairs where on the x-axis it's the sequence, and on the y-axis it's for every point in the sequence, it's the point that happens a certain lag later, like 2 lags later, or 3 lags later, or 4 lags later. So I have to do this correlation for every single one of those lags. And I see, do I eventually get like things to line up where a point in the sequence is a really good predictor correlation-wise of a point down in the sequence. And if that happens, then we say that there's autocorrelation. So self-correlation is what autocorrelation means. So it's a way to test for correlations across multiple different distances in the sequence. But it ends up being problematic because what we'd ideally like is one single test, not if I have 1,000 sample sequence, I don't want to have to do 1,000 correlation plots for every single lag. So, and then it becomes a fishing expedition because if one of them shows a correlation, then I have to say, well, did I reach my 5% error? Like maybe that correlation was just a mistake. So in principle, we like the idea of autocorrelation tests because we don't want one point to predict another point. And the way to directly test the predictive ability of one point to another point is just to look at their correlation. And so instead of using autocorrelation, though, we use a more practical set of tests called runs tests. And there are a wide variety of runs tests. The one we learn in this class and this semester is runs above and below. If you happen to have notes from other classes taught by other instructors, some people use other runs tests, like runs up and down. I've had semesters where I've given somebody a runs above and below on the midterm, and they've done a runs up and down, even though I don't teach a runs up and down. So it shows that they picked up other materials from other instructors and learned that material. And so so we're really using the above and below in this class. And so make sure you learn what I'm about to teach you, or if you're learning it on your own, learn the above and below and not the up and down. But they're all really similar in how they work. And you're going to find that programs like MATLAB, R, et cetera, have got runs tests all built into them, all pre-implemented for you. And you can choose up and down, above and below, et cetera, et cetera. So what is a runs test and how does it work? Well, I'm going to do a list of 30 numbers, just again, like I did before. Now, in this case, I am going to calculate the mean of the numbers. Now, I'm not a sadist. I am not going to have you calculate a mean of 30 numbers on a midterm. if you need the mean, I will give you the mean. If you don't need the mean, I might give you the mean just to not like give something away. But if I forget to give you the mean, you probably don't need the mean. So if you think you need the mean and you start calculating the mean of 30 numbers, something's probably wrong. I never would intend for any of you to calculate the mean of 30 numbers on a midterm. So if you need the mean, I'll give you the mean. So what do you do once you've calculated the mean or were given the mean? You turn every number, you leave the numbers in the order that they're in. That's super important. And then you convert every number into a 0 if it's below the mean, or a 1 if it's above the mean. So here, notice I got 0, 0, 1. Well, that's because this 1839 and 3803, those are my 0, 0s because they're all less than this 6760. But 8629 is greater than 6760. So that's where I got the 0, 0, 1. So every number, compare to the mean. If it's below, give it a 0. If it's above, give it a 1. And that's how I get this string of zeros. Everybody see that? Any questions on that? Just a little predicate there where above the mean is a 1, below the mean is a 0. All right, so then what do? Now we have to calculate the so-called number of runs of values above the mean and values below the mean. And so what do I mean by run? Well, here, this is a diagram where I've taken my 001 pattern and I've broken it up into its 19 runs. So what runs are just sequences of the same value. So 0, 0 is a run because it then is next to 1. 1, even though it's only a single number, is a run because it then switches to 0, 0. So basically, every time you switch from 0 to 1, you end, or 1 to 0, you end a run. So in this string of 30 numbers that are 0 or 1, there are 19 runs. All right, does everybody see that? Are there any questions about what I mean by a run? Questions online? It's sometimes hard to see at first what I mean by runs. All right, so if I were to take all these numbers and just kind of collapse them together, I would get the sequence that I started with. Okay, so then I can also count the number that are above the mean and the number below the mean. So there are 17 ones and 13 zeros. That's what I've got here. All right, so now what do I do with that? Well, under the null hypothesis, if I know the bias in this data, in other words, if I know the kind of how fair this this coin toss is here, which I can do by calculating, like if I know the number of above, the number of below, then if I think of these zeros and ones as outcomes of a weighted coin toss, I can calculate the weight of that coin just by knowing the number of above and below. I can do that by just, I can calculate the ratio there. I can figure out the probability that it would land above or below. So if I think about above or below as outcomes of a coin toss, then this is how I can parameterize that coin toss. Now, under the null hypothesis, the outcome, even if it's an unfair coin, if I flip that coin, then I will get a certain distribution of runs. And so you can work out that for an independent coin, for a coin that doesn't matter if it's fair or unfair, but with every flip of the coin, it then has an independent draw, which is not related to the previous draw at all. You can figure out what the null distribution of runs is. And it turns out that the mean number of runs you should get for any such coin is described by this expression here. And this is an expression that it's a good one to know. So I put that one like on your cheat sheet, is that for runs above and below, you need to know this expression, which is the mean number of runs. And this is the variance in the number of runs. So it's this ugly expression here. And so I can calculate, I should get an average of 15.7 runs with a variance of 6.9772. All right, well, that's great because now I can do a z-test. So the idea here is I can turn this variance into a standard deviation, and I can calculate a z-score for my observed number of runs. So remember, I observed 19 runs. Well, I'm expecting 15 runs on average with a standard deviation of the square root of this thing. So that's all I calculated here is a z-score. There's my 19 observed minus my 15 expected divided by the standard deviation. That gives me a z score of 1.2367. So from there, I can look at my Z table, and I can say that this is where you have to remember the difference between one tail and two tail, because on the Z scores, it matters to me whether the number is negative or positive. Like either one's just as bad. So if this was negative 1.2367, it'd be just as bad or good as this being 1.2367. So in the Z test, when I give you an alpha of 5%, you have to look at the half of that, so 0.025 row, because usually I'm going to give you a one-tailed critical normal values. So if I look at that, I see that for a one-tailed normal, the 2.5% level corresponds to a critical Z of 1.96. And that's a number you should eventually just burn into your brain, 1.96. For those of you who've already known that the confidence interval is twice the standard error of the mean, that 2 comes from the 1.96. So that's just a number that you should just eventually memorize. Not necessarily for midterm or whatever. I'll give you these tables, but it's a number you'll see over and over again. It's a really important number. And so I compare 1.23 to 1.96. And I say that, well, so because 1.23 is less than 1.96, then I do not reject the hypothesis of independence. So if it was greater, then these are likely not independent, but since it's less, then I'm not rejecting the hypothesis of independence. Questions? Yeah, so because, and this is just a standard thing with the Z test, is that, I mean, in short, if, let me see if sometimes this works in this room, it works in all the other rooms, but it doesn't seem to work really well in this room for whatever reason. Let me tab over to Zoom real quick and see if, okay, maybe that'll work this way. So in a Z test, see if I'll bring back the controls. There we go. So what I'm saying is that in, I think one of these is a whiteboard. Well, I'll just draw it on the side here. All right, so if I think about my my normal table, my standard normal, then what the Z test is testing is, so this is effectively null. So if my null hypothesis was true, then I would get a standard normal of, I would get a standardized score here, a Z score of 0. So if I get any number that is slightly bigger than 0 or slightly larger than 0, I have to ask, is it a significant deviation from null? So I can deviate in both directions. So this is what I refer to as a two-tailed test, because I care about deviation in both directions. But typically, we give you one-tailed tests here. And so with a one-tailed test, this would be if I only cared about deviations in one direction. So the way you get critical values for a two-tailed test from a one-tailed test is you cut the alpha in half. So I asked you for an alpha of 5%. So in your one-tailed test, then you actually look for 2.5%. Does that make sense? Oh, no, yeah, that's fine. I'm sure that there might be other people with the same question. All right, so any other questions about the runs above and below the mean? There's also other variants like runs above and below the median. People will do that as well. It doesn't quite matter what central point you choose. You can, because really once you get this kind of these zeros and ones, then the rest of this follows. Because these 0 and 1s, regardless of which number you choose to pivot on, should, if they're independent, will also follow along these lines. So whether you use median or mean, or mode, I guess. Okay, so that's how we test for independence. So let's clear that. All right, so then the last thing that we talked about last time was the LCG. Hopefully this makes sense, how to plug these numbers in. You should know this formula. I probably on a midterm might ask you, I might say, here's a multiplier, here's an increment, here's a modulus. Here's, here's a feed to generate a couple of numbers. On a multiple choice test, I might ask you for the numbers, or I might ask you for like, what's the third number in the sequence? And so you might not specify all the numbers, but you'll have to generate the third. When you're doing these, the only thing that you might get caught up on is that remember that the seed is not the first number. So the first number is after you take the seed and run it through, and then whatever number you get out from that, divide that by the modulus, and that's the first number. So it's sort of, you wouldn't use the seed because everybody knows what the seed is. You kind of want the number to be a surprise. So the first number is after you plug in the seed. Okay. And so the nice thing about the LCG is it can have long periods that'll fill out the full modulus. They'll be independent, they'll be uniform, all that's great. The problem with the LCG's independence is that it can have short cycles. And so if we want really long cycles to make this truly an independent random number generator, we use the combined linear congruential generator, where we take two linear congruential generators, basically take their sum or their difference, and the result ends up being one that has a much longer period, a much longer cycle length, and has all the benefits of a normal LCG, but much longer cycles. So it has even better independence. So that's the big thing to know, is that an LCG has the potential to give us independence and uniformity, but has short cycles. To make them longer cycles, you can use a combined linear congruential generator. So any questions about that? So behind the scenes, when you draw a random number from Excel or whatever, it's a good chance that it's using something like this. They can use more exotic things like Mersenne primes and stuff like that, but this is sort of where everybody starts. Okay. All right, so in that case, let's start on some new stuff here. So I want to make sure that we at least get the analytical inverse transform method. As I mentioned, you go into Arena, as you've seen now, and you can go in and you can specify expressions for random distributions or for timings, for example. So how long do things take? And it has a bunch that are already provided for you if you know the parameters, but sometimes you might need to pick one that's not in their list. And so we need to figure out how to generate an expression so we can put any distribution that we want there. So we've already seen in a previous lab how to generate a uniform distribution between, let's say, 2 and 4 in this case, using a uniform distribution that is provided for us where it's distributed between 0 and 1. And so we just need to generalize that. So if we can have a random number distributed between 0 and 1, then how do we turn that into any other distribution that we want? And I've talked about this before, inverse transform sampling. If we've got the CDF, we can invert the CDF, plug in the uniform number into sort of the back end of the CDF or the inverse CDF, and then what pops out will be a nicely distributed set of numbers. So how do we do that in general? And this is what you do in this latest homework. And so you first obtain the CDF. If I give you a PDF, you integrate it to do the CDF. If it's invertible, which in many cases it will be, but in things like the normal, it won't be, you let some dummy variable called R equal to the CDF, and then you invert it. So in other words, you solve for X, which is buried inside the CDF, so that it becomes a function of R. And then you take what pops out of that, and then you can plug in a pseudo-random number that's distributed between 0 and 1. If you plug that into the inverse that you got out of here, which I call F inverse R, that will be a sample from the desired distribution. So that's the flow of how you get from PDF to samples of that PDF using the inverse transform technique. So a simple example here, let's say I want to draw from the exponential distribution. Here's an exponential's probability density function. It's 0 for all negative numbers. It's this thing for all non-negative numbers. And so I just need to take the integral of that. Now I have to be careful because the integral goes from negative infinity to X. And this thing is 0 up for all the negative numbers, and then starts with this only for the non-negative numbers. So I have to break this up into a piecewise integral. So for everything less than 0, I integrate this blue guy. And for everything greater than 0, I integrate the blue guy up to 0, and then the red guy from 0 to that point on. That's the twist there that you've got to make sure that you remember to do. For this one, it doesn't matter that much because the thing in blue is 0, and so that's going to fall away. So the integral of 0, this is just going to end up being 0 for all the negatives. This one up being dropped off as if it wasn't there. And so I end up just getting this, and that's my cumulative distribution function for the exponential. So that's our simple example of how to do a piecewise integral. Now, if you don't remember how to go from here to here, it's just a little substitution, and I'll put it in a little box here for you to review. This is how you integrate an exponential with sort of an interesting set of things in the exponential. I'm just going to let u equal to things in the exponential, get a du equal to the relationship between du and dt, do a bunch of substitutions, and that's how I get from here to there, or in other words, from this piece to this piece. So that's just kind of review of calculus. I won't spend a lot of time on that, but if you're having trouble getting from here to here, I recommend going back to this slide and reviewing how to do that substitution. All right, so now that we've got our CDF, we want to invert it so we can generate those random numbers that are from the exponential distribution, those random variates. And so for the exponential, it turns out that if I look at the inverse, the entire 0 to 1 domain gets mapped to my range of the random variable, 0 to infinity. And so I only need to worry about one of the parts of that integrate by parts. In other words, even though this CDF here has got 2 parts in it, this part here has no probability math, so I'm only going to focus on the bottom part. So what I do is I set R equal to that bottom part, and then I just solve for X. And so I go through a series of algebraic steps, and this ends up being my inverse CDF. And so, like I said, this just came from solving for X, and then and then I got rid of the X and replaced it with this F inverse negative or R, and that ends up being my function there, where now if I draw a bunch of random numbers distributed between 0 and 1, if I plug them into this formula, I will get numbers out that are distributed exponentially. So any questions on that example before we go to a more complex example? Questions online? Okay. All right, now, in practice, whenever we generate exponential random numbers, we actually drop this 1 minus. And that's because 1 minus r is also distributed like a uniform number between 0 and 1. So because r and 1 minus r have the same distribution when r is uniform between 0 and 1, then it's more computationally effective to use this formula. So if you ever see an exponential, like if you go to Arena's help files, for example, and you see how it's generating its exponentials, you might see this formula in its help, and you say, well, that's not right. Shouldn't it be a 1 minus r? Well, it's because 1 minus r and r are distributed the same way. So it's just cheaper computationally to use this formula. It doesn't come out of the math exactly. It's just an optimization. So that's why we typically see this formula here. All right, so I plug in a bunch of my numbers and I histogram them. And here's my histogram in red. Here's my expected distribution in blue. And it's exactly what I want here. So in Arena, I can use this expression or I can use this expression, and they give me the exact same histogram out. So that's how I generate my exponential. All right, so what if I want to do a more complicated thing? Like I want to draw numbers for my triangular distribution. This is a little bit more like the homework. So here I've got this ugly piecewise probability density function. It's 0 for everything less than A. It is 0 for everything greater than B. It peaks at this intermediate point C. And this line here is described by this expression. And this line here is described by this expression. So I need to solve for the CDF and then invert that CDF. So how do I do that? Well, I have to integrate this thing from negative infinity to x, but it's got a whole bunch of pieces. And so I have to break it apart a bunch of times. And so I've got for when x is less than a, I'm just integrating this piece up to x. When x is between a and c, I take this piece from negative infinity to a, and that's just a constant that I add. And then I take this piece from a to x, and then in the next section, when x is between c and b, then I have to add on another bit. So I take the constant from negative infinity to a of this piece, the constant from a to c of this piece, and then all that's left over is this little residual marginal from c to x of this green piece. And then I go on and on. And so if I step through that process, then I can plug in the zeros in the sort of the easy pieces here. And so I integrate under 0, and for both of those, they fall away. And then I'm just left with integrating these ugly pieces in the middle here. And so I'm going to put in those pieces in and take those integrals. And then I'm going to get this integral from a to c. It gets simpler when it's just the constant piece here. So there's this integral from c to b. And then this thing, if I did it right, these two things should add up to 1. So if I simplify that all together, then I get 0 as I'm expecting on the left, 1 as I'm expecting on the right. And I should see that this thing, if I plot it out, is non-decreasing and should be exactly like this function here, where it'll rise, have an inflection point, and then kind of decelerate after that. And so if you do plot that out, I think that's what you'll find. All right, so any questions about that part, the piecewise integration of this ugly CDF? All of the breaking things up at those boundaries. That's the major difference. Questions online? All right, so with this one, we have another wrinkle when we take the inverse because of all these squares. So that's the other thing that you can, like, I test you on a little bit in the homework and so on, is we have to remember that when we take the square root of something, we get 2 roots out, a positive root and a negative root. We need to choose which one we want. So how do we invert this thing? That's the next step here. Okay, so here's my CDF up here. I need to figure out my ranges first, how to map X ranges to R ranges. And so I can see here that if I plug in from X is equal to A into this thing, I will get 0 out of the CDF. And if I plug X is equal to C into this thing, I will get this C minus A, B minus A out. So that is how I map this X range, A to C, to this R range, 0 to C minus A over B minus A. Then if I go to this range and I plug a C into this thing, I'm going to get C minus A, B minus A. If I plug a B into this thing, I'm going to get 1. So that shows me my correspondences between this X range in my random variate and this R range in my pseudo-random number generator. So, so that tells me which 2 parts I need to invert. And as I invert them, which correspondences do I need to make sure stay together? So, so I have to just remember those 2 ranges. And so that's what I'm going to do. I'm going to do those 2 inverse problems. And so I am going to set R equal to this for this X range. And I'm going to set R equal to this for this X range. And then for both of them, I'm going to solve for X. And I'm going to make sure that I draw my square roots so that the resulting X ranges that come out match for the right R ranges. And so if I take this thing, I can do a little bit of algebra. So I go from this mess here to this mess down here. And then from this mess down here, I can solve for X. And I get this random number generator or random variate generator. So just by solving here. Now I've chosen a plus here and a minus here. So again, there's a square root here. So I could have chosen a minus here and I could have chosen a plus down here. I have to look at the ranges to figure out which root to choose. And in this case, I know that from 0 to C minus A, B minus A, I should get a number that goes from A to a number larger than A. So that tells me that since this square root's always positive, this should have to be a plus, because otherwise I'll be generating variates in the wrong part of the range. And likewise here, I know that from this range, C minus A, B minus A to 1, that generates numbers that go from C to B. And the only way that I can generate numbers that top out at B is if this is a B minus a positive, not a plus. And so that's how I choose the plus and the minus, to ensure that this range maps to A to C, and this range maps to C to B. So any questions about that? Choosing signs for these square roots, which comes up a lot when you're taking these inverses. Questions online? Okay. So with that, I can then implement this. So in Arena, fortunately, they have something called TRIA, which implements it for me. But if I wanted to implement it manually, I can do that in Arena by implementing this expression that I just wrote down here. How would I do that in Arena? Well, it's a little ugly. So I'm going to zoom in here so you can see that. So I can create a little assign block, and inside the assign block, I can assign a variable R to a random number draw. That's a shortcut for that in Arena, RA. And then this ugly mess here is something that if you look closely at it, it's the sort of the top case times R is less than a condition, plus the bottom case times R is greater than a condition. In other words, I can take that conditional, that if, and I can turn the less than condition into something that evaluates to 0 or 1 that masks off one of them when it's 0. And then the other one, which is either 0 or 1 in the other case, which masks off the other one. So it's a way for me to combine that piecewise inverse CDF into one line that I can implement in Arena without having to do any ugly if-then logic. But you get this kind of mess here, which is why it's really nice that when you need to implement triangular distributions, which is pretty common, that Arena's already done all the work for you. So you can just implement it there. But if it was a more exotic distribution that Arena didn't have, you might be forced to write your own using the inverse transform method like this. All right, so any questions about any of that? How we go from uniformity from 0 to 1 to anything we want using inverse transform. Okay. All right, so so a couple things to note about that. So in practice, if you're going to need to write your own inverse transform generator, it's rare you have to do the inversion yourself. Because if you were to look up most distributions that are out there, even distributions that aren't in Arena, somebody's probably done the work for you. And so if you were to Google for the quantile function, then you'll be able to find that that's another name for the inverse CDF. So if you go to Wikipedia, for example, and you look up pretty much any probability distribution, over on the right-hand side where they got the little quick reference on the distributions, there should be one row that says quantile function. And that quantile function is the inverse CDF. You can just copy it down, and then you've immediately got a generator for that random variable. You just plug random numbers into the quantile function, you get random variates out. So that's why I've got this kind of example table here, which you're not going to need to memorize this table, but I'm just kind of showing you that for things like exponential, uniform, Weibull, triangular, then these are the quantile functions that have been pre-calculated for you, so that if you really ever needed to generate these, you can just grab these things, dump some random numbers and where the R is, and then immediately you get the samples out. Done. So that's often really automatically done. Okay, so and the other ones I want to make sure we cover is discrete random variables. So I've talked about this a little bit. I could give you a probability mass function on a midterm, as I often do, and you would then need to construct the cumulative distribution function. And once you've got that, you can now generate discrete random variables using the same sort of method. And the idea here is I've got my CDF that I've plotted out here as my 3 outcomes. If I invert it, I just sort of took that thing and mirrored it across the diagonal. So if I imagine a diagonal line there, I'm going to go back a slide, forward a slide, imagine me folding this thing over across that diagonal line. Then that's all that I'm doing when I say I'm generating this inverse. And then I can plug in numbers from a random number generator from 0 to 1 in, and then I can see where they hit, and that tells me which outcome comes out. So on a midterm, I might say, here's a random number generator where I could give you a string of numbers drawn from a pseudo-random number generator, and then I could ask you to generate 3 discrete outcomes from this probability mass function. And you'd have to be able to do this process. And with the 3 numbers that I gave you, like 0.54, 0.9, 0.2, I'd be able to look up and then figure out what the 3 outcomes would be that would correspond to that. That would be a common thing that I might do there. So the CDF basically gives us boundaries for transforming this thing into a random variable. So if I were to look back at the CDF, this tells me anything from 0 to 0.2 gives me outcome 1. Anything from 0.2 to 0.7 gives me outcome 2. Anything from 0.7 to 1 gives me outcome 3. And so that's basically, if you've got the CDFs and you've got the random numbers that I've given you, it's easy to change the random numbers into these outcomes in the right proportions. Okay, so, and that's all I'm sort of saying here. So I've got 0.2, 0.7, and 1. So this tells me the ranges for outcome 1, for outcome 2, and outcome 3. Now in practice, when you do this in Arena knows you're going to be doing this a lot. And so they've created a function called disc. Now, the tricky thing about disc, which you should remember, and this is also a midtermable thing, is that disc encodes the inverse CDF. And so that means that the CDF values come first, outcome values come second. So in disc here, you're going to always see that the odd numbered arguments are going to be between 0 and 1 and increasing. The even numbered arguments generally are increasing, but I don't think have to be. I don't think it'll complain if they aren't. So here I can see that my outcomes are 1, 2, and 3, and they show up as the odd numbered arguments. Their cumulative distributions show up as the even number arguments. So you don't put the probability mass function into the discrete function in Arena. You put the cumulative distribution function. And that's something that's key to remember inside disc. So if you got disc, you can dump that in and it'll automatically draw it for you. Now, it's also possible that when you take data, you might need to generate numbers that are consistent with your data, but they don't have a distribution for them. And so in that case, you can sort all of your samples and turn them into a kind of discrete probability mass function where the sample corresponds to a probability, which is just its rank in the order divided by the total number of those samples. So if I have a bunch of outcomes that are sorted, then I can think of their probability mass function as 1 over the total number of samples, and their cumulative distribution is just the accumulation of those things. And that allows us to just basically take data and plot it. So these are some outcomes here. I can actually use a disc function in Arena to be able to generate random samples that have the same proportions as the data that I see there. So it will have it, if there only are 8 outcomes here, there only will be 8 outcomes here, but they'll have the same proportions. The downside of this is normally when you take these data, you actually want things to be generated in between. And that's why Arena has created something called Cont, which just takes that sample CDF and it interpolates it so that if you were to draw from the interpolated CDF, you actually get things that almost looks like these like piecewise uniform things that at least fill out the range in roughly the same proportions as the numbers that came out of the data that you sampled. So that's an example of how we can go from a discrete probability, or from sampling discrete random variables to sampling from data. And that's basically, there's a couple other special cases in here that I'm not too worried about. As you're reviewing for your midterm, I recommend, it's not a bad idea to take a look at these, especially this geometric distribution one. The rest that I've got in here was kind of bonus information about things like, well, how the hell do we sample from a normal distribution, considering that we can't invert a normal CDF? It's not invertible. And so I kind of talk about the different ways to do that here and some other things. And so the big takeaway messages that I want you to take out of this right here is that inverse transform technique, very powerful. When the inverse is elusive, there are other techniques that are out there that I haven't gone over here, but one of them is called the normal to anything method. So if you see NORTA, that's basically a general method that allows you to turn normal random variables into anything else, and that allows you to generate correlations. And ARENA has built-in functions to sample from the most common continuous distributions, and you can also use disk and cont to approximate a wide range of others. So that's kind of the big sort of takeaway here for this inverse transform method. So let me give you an attendance question since it is at 45 here. And I'm happy to take other questions on Thursday, as will be the midterm review. But I'm also happy to take questions after class if that works for you. So the question I have for you here is, what is another name for the inverse CDF? What is another name for the inverse CDF? And there was a question online, do we get a note sheet for the exam? You get 2 pages for stage 1, double-sided. Hand-produced or self-produced. And so if you want to type it, that's fine, but I don't want you to have any screenshots or any direct facsimiles. You can draw graphs yourself, you can type it yourself, but you've got to produce it yourself. And that's all I got for you. So if you have any questions, feel free to come up. Otherwise, we'll see you Thursday for the midterm review. Any other questions online? If not, I'll start packing up the Zoom. Okay, in that case, we'll see everybody Thursday. Have a good week.